So our next talk is remote. It is on the topic of prototypical collaborative filtering for few-shot item recommendation. Yeah, can you hear us?
Yeah, I
Perfect.
can hear you.
So,
cool. So thank you for the introduction. Hey everyone, my name is Aravind, and I'm a PhD student in computer science at the University of Illinois, Urbana-Champaign. So today I'll be presenting our work on few-shot recommendations. This work was done in collaboration with my advisor, Sundaram, and other members of our crowd dynamics lab, Junting and Adit. So here today we examine the typical implicit feedback setting with historical user item interactions. And the goal is to generate personalized item recommendations for each user. So most neural collaborative filtering models, including matrix factorizations, follow a general framework where we have preference encoders to learn user and item representations, where here the NCF models might adopt a variety of different strategies, such as using latent embeddings, meaning matrix factorization, or we have autoencoders and graph neural networks for this purpose. And then we have an interaction function that computes a pairwise relevance score, which measures similarity between the user and item's latent representations. And the final model is trained on user item pairs using a variety of different recommendation objectives. In our work, we address a fundamental challenge of item popularity bias in collaborative filtering. This challenge arises due to the long tail interaction distributions, where a majority of items in the tail have very few interactions. So empirically, when we examine model performance, if you look at item we call at K, where the goal is to evaluate the probability of ranking items accurately within the top K, when we examine the model performance of popular neural recommendation models, we see that for different item groups sorted in increasing order by their interaction count, we find that neural models overfit to popular items, and the performance is much lower for the long tail items in the inventory. So this indicates like a clear popularity bias and shows poor resolution in ranking relevant items within the tail. So this is the classic long tail challenge that we address in our work. So there's been some prior work in addressing this long tail challenge for a while. So some of these approaches include data rebalancing strategies like oversampling and undersampling, but each of them come with their own trade-offs, like oversampling would result in overfitting to the tail, while undersampling the head items would discard useful information. Another common approach is using item-to-item co-occurrence information as a mechanism for regularizing latent factor collaborative filtering models. So an example could be using the co-occurrence matrix as a joint factorization model or imposing static regularizers. These methods often have some restrictive modeling assumptions. And another common approach is using data augmentation for sparse items in the tail through adversarial rating generation techniques. These methods often tend to be computationally expensive and do not scale well to really large-scale inventories. The most common approach that's been explored by a lot of work is the use of external side information to overcome limited interactions. For instance, in the last talk, we looked at the example of knowledge graphs being used, and a lot of item attributes and side information is commonly used to address sparsity challenges. But then side information is typically application dependent and may not be easily available. So in our work, we take a different perspective on the long tail challenge, and we formulate long tail item recommendations using a few shot learning paradigm. So we formulate a K-shot item recommendation problem where the goal is to generate recommendations for users over few shot items where each item has up to K interactions. Here, K could be very small, like say 5 to 10. And we adopt the meta-learning paradigm in our work to train a meta-learner that learns to recommend few shot items. Here, the meta-learner is trained over a collection of training tasks that are designed to simulate the K-shot recommendation problem. Here, our framework adopts the metric-based learning paradigm, which is inspired by a lot of work in the computer vision domains, especially. Here, the approach is to define a shared metric space of users and items, where the meta-learner can construct an item prototype just from its K user interactions. And now to recommend relevant items, we retrieve the nearest item prototypes for each user, and that is used to recommend items. In the past, gradient-based meta-learning has been explored in the recommendation context, mainly in the settings of zero-shot learning or basically cold start setting with site information. However, ours is one of the first to explore the few-shot setting with few interactions, and especially introduce metric-based learning approaches. So next, I'll briefly introduce an outline of our work. Okay. Our framework has two stages. The first stage is we pre-train a neural base recommender. So this base recommender could be any neural model. It could be a matrix factorization model or an auto encoder-based model or whatever. And the goal of this is to learn high quality user representations and item representations that mainly capture preferences over items in the head and can also infer relationships amongst different items in the inventory. In the second stage, we train our few-shot recommender, which has two components. First, we extract a compact representation Z of the item-to-item relationships that were learned by the base recommender. And we do this using, okay, I'm not sure why the slide advanced. Let me just go back. We achieve this using a stochastic knowledge distillation strategy. Then our few-shot learning model, RF, which is first initialized using the parameters from the base recommender and transfers this knowledge Z from the base recommender and learns to construct discriminative prototypes for few-shot items. Overall, the framework follows an episodic training setup which mimics the interaction distribution of few-shot tail items within each meta-training task. So each item in the tail has very few interactions, so maybe up to 10, and for each meta-training task is defined by a support set and a query set. So we first sample a set of n items from the inventory, which in this example could be, say, 3 items, just as a toy example. And we now define a support set and a query set based upon the items in this particular task. So these support and query sets are analogous to training and testing within the same task. Here, for say an item P, the support set SP contains K interacted users that are subsampled from its interactions, and the corresponding query set includes another set of K prime users. And the goal of the meta learner is to construct a prototype or an embedding from the interactions in the support set, and it's evaluated based on the interactions in the query set. So this follows a training and testing framework within each task that is being sampled. Now the question becomes, how do we learn these prototypes? Is there an effective strategy that we can use? How do we learn to construct these prototypes? So an initial approach to construct prototypes is really simple. Like, we can just take the mean or the average of the K user embeddings of the users in the support set. However, a simplistic averaging strategy might be noisy and may not be able to discriminate across diverse items within the long tail. So for this purpose, what we need is an inductive bias to avoid the risk of overfitting and yet have sufficient expressivity to learn useful prototypes. So for this purpose, we summarize the knowledge from the base recommender using a set of group embeddings. So these group embeddings could be visualized as centroids of overlapping clusters of items. For instance, each centroid may represent a contextual factor, like say a restaurant type, say a cafe, or say a location, maybe Chicago. And sometimes items could lie in overlapping clusters. An example being, say, cafes located in Chicago. And we then view items as mixtures or learnable mixtures over these group embeddings. And this enhances the prototype by relating it to other relevant items using the cluster centroids. And the group embeddings are trained using a knowledge distillation approach. You can refer to some of these details in the paper. So since our approach is specifically designed for few-shot recommendations, we compute overall ranking scores by interpolating the scores or the final predictions between the few-shot model and the base recommender. We find that overall, in terms of overall recommendation results, our approach has around 5% gains over state of the art. But where we see significant improvements is when we examine model performance across items with different popularity levels. And we noticed that especially in the long tail, when we look at, say, groups G1 to around G8, that's when our performance gains are really significant when compared to different base recommenders. So here we compared against BPR, which is a matrix factorization model, and DAECF, which is another popular neural collaborative filtering method. And we observed very significant gains over the tail while not really compromising on the overall model performance. So that is especially significant because you generally do not observe a lot of gains in terms of the overall performance. So in conclusion, we find that our approach, ProtoCF, can learn lightweight few-shot models that are tailored to items with interaction sparsity. And compared to gradient-based meta-learning models, one advantage of metric-based meta-learning is the lack of any fine-tuning to handle any new items at inference time. So maybe you have a new item with a few interactions. It's easily possible to just compute the embedding directly without any new gradient updates. This paradigm is fairly general and can be extended to handle interaction sparsity for users as well. And I'm not sure why, again. So our code on data sets will be publicly available on our GitHub repository in a few days. So stay tuned for that.
Thank you for this great talk. We now have a few questions from the audience. So first, one question was by Scott. So your last plot in the paper seems to say that the results are independent of embedding size. Was that true?
Let me see. So you're talking about the last plot in the paper? Let me just find that. No, so the results are not independent of the embedding size. So the last plot in the paper, it talks about task size, which is with respect to the number of items that are being sampled within each training task. So for instance, in every meta-training task, number of items that you sample. So that's probably the experiment that the question is about. We did not do experiments with respect to embedding size in this paper because our focus was more with respect to the long tail challenge. So it wasn't so much as to improving results, but in our preliminary results, like comparing different embedding sizes, we observe mostly a similar gradation. Like typically when you increase the embedding size, model performance goes up, and then you have a diminishing returns beyond a point. So that's as following as expected lines compared to all the previous works.
Thank you. We have another question by Shivam. So after fine-tuning the base learner with few short tasks, does the performance on user item interactions, which was originally used to train the base learner, drop, or does it remain consistent even after fine-tuning?
It's a good question. So so in our approach, what we do is we essentially transfer knowledge we initialize the few-shot model from the base recommender and then train it on the few-shot learning objective. So when we evaluate just the few-shot model in terms of the overall recommendation performance, the performance of that goes down. But then in terms of the way we generate predictions for our model, we interpolate results or ensemble the predictions from the few-shot model and the base model. So in that way, we are able to effectively make sure that any loss in performance over items in the head is compensated by the base recommendation model itself. So in that way, it's still a post hoc strategy of ensembling, but we find that even a really simple strategy like this is still able to do extremely well on the tail without compromising overall results. So that shows the significance of the few-shot recommendation model itself.
Thank you. I think we have time for one more question. This question is by Joe. Can you optimize the learning for a new user by recommending items with highest information gain in the model? And how would you identify these items?
So I think that's a good question, especially because for new users, although this model is designed for the perspective of items in the long tail, I would imagine that the model can be flipped on the side and be used to handle the long tail of users. So in that context, maybe information gain could be an interesting perspective that we could bring in to design how the model is learning. So that's definitely something that could be explored in the future. But I think what will be more challenging is to see a framework that can simultaneously handle both the long tail of users and the items, because that's commonly observed in most online interactions. So that would be something that's more challenging to handle.
Thank you once again. And with this, I would like to conclude the talk, and I would like to encourage you to continue the discussion online because there are some more questions there.
Great.
Thank you once again.